Okay, so average velocity. The first page is pretty easy anyways. What's the goal here? Okay, average velocity is our total displacement over total time. So when we're averaging, right, it's really like we're looking at the straight line, right? Not instantaneous. What's our total distance over our total time when we look at average? So on a position time graph, it's going to represent the slope. So if this was, so in this case, it'd be S2 minus S1 over T2 minus T1. So the slope of the secant line. Connecting the 2 points, right? We rarely will look, basically never, will use average velocity. More importantly is instantaneous velocity. What's more interesting is I would like to know my rate of change at any specific time. So at 2 seconds, what's my rate of change? What's my velocity? At 3 seconds, what's my new velocity? Okay, that's way more exciting to look at. And so that's pretty easy to get if we know derivatives. Okay, because we know the slope of the tangent is our derivative. And so the slope of a distance time graph will be our velocity, the change of distance over change of time, instantaneously. So this is the velocity of at 1 instant in time. It represents the slope of the tangent line. So it's the limit as the change of t approaches 0. Yeah, in math, it's one thing that really bothered me too in school. In physics, it's D. In math, it's S. That's all the, so it's, yeah, it's, and it's not even speed, right? It's S is distance. So in mathematics, they don't always work together, those two sciences, the math and the physics. Sorry. Okay, V and A are the same, it's just position. Position is, yeah. Okay, so that's velocity is the derivative of a position. Or equation. Okay, so our S prime of t is our velocity. The derivative of our speed or position time function will give us our instantaneous velocity. So velocity always indicates the direction of motion. Okay, so let's look at this guy. This is a position and time graph. Okay, so I'm going to give we have A, B, C, D. So looking from A to B, is our velocity going to be positive or negative? Positive. Okay, it's positive. It's an upward slope, right? We're talking about slope. Slope is our velocity. What's the slope of this line? It's going to be a positive slope. At B, what would it be? Yeah, it would be 0. Oops. Our speed is, or instantaneous velocity is 0. From B to C, it would be, our slope is negative. So velocity will be negative. Tells us direction. And C to D, oh, at C, thank you, 0. C to D, positive. Okay, let me just fill on top. If our velocity is greater than 0, then it is moving in a positive direction. Well, it's not differentiable at that point then. You can't figure out its instantaneous velocity then, if it's a cusp. Okay, so example, forward, upward. Okay, If v equals 0, then it is at rest. And if it's less than 0, it's moving in a negative direction. So, yeah, backward, downward, southward. Sorry. So it's just, so it would just be east and west, right? East and west. So like up here, here's your position. So the top would be positive, would be east, bottom would be west. So going in towards an east direction, west direction, east, right?
But if it was moving starting west, and then switches to east, what are we moving at negative 3? It starts at negative, and then starts moving into a positive.
You're confusing like relative to the origin. So slope is going to tell us help tell us the direction. Okay, so you can start down here, but that doesn't mean you're moving that direction. As long as your slope is positive, you're moving in an eastward direction. Even if you start down here, you're just starting wherever your origin is that you're calling, you're starting to the west of it. Okay, oh yeah. Okay, by using both the positive position and velocity, okay, so by using the position and velocity functions, we can determine whether the object is moving towards or away from the origin. So if S and V have the same sign, then it's towards moving, same sign, it's moving. So then the product of them would be greater than 0. That would be away from the origin. And if they have the opposite sign, it's moving toward the origin. And we'll look at a problem like that to make sense of it in a second.
What's it mean when you go a velocity?
Okay. So a stone is thrown from a cliff 80 meters high until it reaches a velocity of 15 meters per second. Yeah. Find the velocity at 1 and 2 seconds. Well, most likely, right, this would be acceleration over here. Well, related to acceleration, negative 9.81. So this equation represents the function, okay, represents the position of the function. So how do we get the instantaneous velocity? So all this information was used to create the equation. You don't have to use it, right? We have the equation. Okay, so given the equation, find the velocity at 1 and 2 seconds. So how do we do that? That would give us position at 1 and 2 seconds. So what would give us the velocity given the position equation? So at t is time, s is position.
So what is position as a function of time?
The derivative is? What is s prime of t? Did you guys say that, but I just didn't hear it? No? Okay, so velocity is the derivative of a position equation. Yeah. So derivative of this guy would be negative 15 minus 2 times 4.98, 4.9, which is 9.8 t.
I don't know. I mean, it's not like a really high number.
Okay, anyways, it's 80 meters. So it's pretty high. It's 80 meters starting at.
Yeah, but it's 80 meters above like a really tall thing. Yeah.
Okay, so what's the velocity? So now we can find the velocity at 1 second. How would we figure that out? Plug in our time. What does that give us? negative 24.8. Why is it negative meters per second? It's going down, right? That's its direction. And then negative 34.6 meters a second.
So 15 must be its initial velocity.
Yeah, it must be.
It must be.
How is it doing to be at 15?
No, it must be.
It must be initially.
Thrown
At.
So,
Yeah.
Oh, well, then we can figure it out.
yeah, that's
Yeah, you could.
pretty use formula stuff.
Okay. Okay. So the distance traveled by car is given by where t is measured in hours and s in kilometers. When did the velocity reach 100 kilometers per hour? So first step here. So not to know when. What's when? Time. The velocity. How do we get velocity from our equation? The derivative. Okay. So our velocity is s prime of t, which is what? 320t plus 20. And we want, when is our velocity equivalent to 100? So we're looking for what is the time when our velocity is 100. So subtract 20, gives you 80. And divide by 320, what does that give you? 1 over 4. What's the unit? No. In hours. It was in kilometers an hours. So that's quarter of an hour or 15 minutes. T is measured in hours and S was in kilometers. Okay, do you want to try the last one by yourself? How about try A and B? And then we'll go through C. Is it the last one? Try A. Yeah, we're almost done. It's a really short lesson today. Okay, I'm sorry. On behalf of all mathematicians, I am sorry.
The guy who decided that.
Okay, give it a shot, guys. Try number 1, A and B. Okay, the position of a particle is given by, so find the velocity after 1 and 3 seconds. So velocity is the derivative of our position. We should have had 2t minus 4. So at 1 second is negative 2. And at, what is it at 3 would be 6 minus 4, which is 2. Direction. Change in direction. Okay, when is it at rest? Yeah? Pardon me? At t equals 2. And how do we get that? What does rest mean? V equals 0. So 0 equals 2t minus 4. Add 4, divide by 2. So at t equals 2. Seconds. Okay, when is it moving in a positive direction? So what can tell us when we're moving in a positive direction? Let's use an inequality there. Here. That's towards the origin or away from the origin. So as long as it's moving in a positive, you could either do when s is greater than 0 or when your v is greater than 0. It's easier for v. Okay, because if it's v is positive, right, it's moving in a positive direction. If our v is negative, it's moving in a negative direction. So we want it, yeah. So we're just solving when is it moving in a positive direction? When t is greater than 2.
So like, okay, I'm sorry. I was confused. I thought you were saying it was wrong.
No, no. Okay, draw. We're going to draw the one-dimensional diagram. So draw a diagram to illustrate the motion. So for sure we want to include 1 and 3. well as 4. Let's go 1, 2. What do you mean? Oh, because we're going to look at some parts. We're going to use parts from Chapter 3 and Chapter 4 in this unit of your textbook. Okay, so in your textbook, we're going to use
Oh, that's in the textbook.
Yeah, yeah, that's why. Okay, so we want a position time graph of our motion. So we're going to put our position at the bottom and our time will right in between. So we need to figure out our positions. Okay, so we're graphing our position with respect to time, but it's a one-dimensional graph. You could do a two-dimensional graph if you want, but let's do a one. How do we figure out our position at these times? S equals? No, that's V. What does S equal? T squared minus 4t minus 4? I think plus 4, right? Or is it minus? Yeah, plus 4. Okay, so at 0, what's our position? 4 meters. Good. At 1, what's our position? So 1 minus 4 plus 4 is 1. At 2, 2 squared, which is 4. So 4 minus 8 plus 4. 0. 3. So 9 minus 12 plus 4. 1 meter. Yeah. Crazy. T squared. Sorry. And it's going to be 4. Okay. So we'll put 0 here. 1, 2, 3, 4 meters. These are our meters. So at t equals 0, where are we? 4 meters, right? T equals 0. Then we're at t equals 1. Kind of wrote over top of myself. I'm doing a one-dimensional graph. You could do either. I'm just showing, this is a new thing. I'm going to show you a one-dimensional graph. You know how to make a two-dimensional graph, right? At 2 seconds, where are you? You're at 0. 3 seconds, you're again at 1. And then we're back to 4. Well, it keeps going actually, so we'll go like that. It's not supposed to be. It's not. It's a one dimension. Yeah. Okay, so this homework today, that's pretty much it. This attached, we could do the quiz if you guys still want to do it. Okay, well, the homework for today is attach this question, number 1, and then these textbook questions. And we'll have the quiz on that after spring break, unless you want to do that one tomorrow, so it's like fresh after spring break.
No, I want to do it after spring break.
Well, I won't do today's right now until you try the homework. Okay.